This week we'll be talking about analysis of variance, which is a statistical technique that allows us to compare the means of multiple samples instead of just two, as we did with the t-test a few weeks ago. So here's an overview for this week's lecture. We'll talk about the history and theory of analysis of variance, and then how it relates to previous topics. Basically, how is it an extension of the t-test? I'll show you a little bit of the nuts and bolts of how it works. We'll talk about some of the key assumptions, which it turns out are the same assumptions as for the t-test. And then finally, we'll talk about how to implement it in R, and then we'll get a little bit more into that in the lab where I show you some more specific examples. Now, just a little bit of review. Earlier in the semester, we were using a t-test to compare the means of two samples that had the same variance, but possibly different means. We were also using the t-test to compare the mean of one sample that we collected to a hypothetical population mean. But again, that sample was coming from a population with the same variance as our reference population. Now, unfortunately, it turns out the t-test was not well equipped to deal with comparisons of more than two samples. So if our question involved comparing the means here, in this example, say of 4 different samples, then we need to find an appropriate extension to the t-test that allows us to do that. Analysis of variance is the test that allows us to do that. And here's just a little bit of history. I think it's pretty interesting. So it was developed by a scientist, a statistician named R.A. Fisher, and he's probably not a household name in the same way that Charles Darwin or Einstein was. Definitely not nearly as famous, but probably more influential than any other scientist in history. So just looking at the types of statistics that he developed and the number of times that those statistics have been cited in the literature, it's almost unbelievable. So we see he developed the whole idea of p-values that we've been talking about in this course and that are totally pervasive in the scientific literature. So just based on p-values alone, his work has been cited over 3 million times. Analysis of variance, over 1.5 million citations. Maximum likelihood, which I think we'll talk about later in the course a little bit, 1.5 million citations, and on and on and on. So when you consider that on average, most scientific papers get maybe 1 citation, if they're lucky. If you get like 10 citations, you're doing a pretty good job, and your science is usually considered somewhat influential. To get upwards of 7 million citations is just unbelievable. And it eclipses almost every other scientist in history. Now, returning to ANOVA, Fisher developed the analysis of variance and the F-test and the F-distribution, which are all used together to test these hypotheses, while studying agriculture. And he wanted to know whether different fertilizer treatments had an overall effect on crop production. And so this was a problem that had more than 2 treatments, more than 2 samples, and so he needed a test or an extension to the t-test. And ANOVA was developed specifically for that. So here's the problem, and this is why a t-test can't be used to evaluate differences between more than 2 samples at the same time. So if we set our critical threshold or our significance level to 0.05, so if we get a p-value less than 0.05, we're going to say that our treatment had a significant effect on the mean. Well, if we only have 2 samples, then our probability of arriving at a type 1 error is 0.05. But when we start incorporating more samples, our probability of encountering that type 1 error and eventually arriving at a false conclusion begins to balloon. And so we see that if we have 10 samples, we have almost a 40% chance of arriving at the incorrect conclusion. Okay, concluding that our treatment has an effect when in fact it really doesn't, and the differences between our samples were just due to chance. So instead of using a t-test, we use analysis of variance to compare the means of multiple samples. And this is usually used for when we have 3 or more samples. In reality, if we only have 2 samples, ANOVA essentially just decomposes into a normal t-test. Now, ANOVA is usually used to estimate the effect of categorical predictor variables on some response. And so when I say categorical predictor variables, this means non-continuous. So we can estimate the effects of, say, being in different groups or in different populations on some response. For example, what is the difference in mean weight between these 3 populations or 3 groups of individuals? Or another discrete predictor variable might be your treatment level. So maybe you've conducted an experiment and you want to know what is the effect of these different treatments. So you have your control, your low dose, and your high dose on some response, say overall plant height. Okay, but it turns out that ANOVA is actually just a special case of linear regression that deals with categorical predictor variables. Later in the course, we'll talk about how to deal with continuous predictor variables. So for example, what is the effect of temperature on your response? And temperature maybe ranges from some negative number up to some positive number, and it has a bunch of values in between. Okay, but overall, ANOVA and linear regression are really just two flavors of linear models. And many of the ideas that we talk about today and next week will also translate into week 9 when we talk about linear regression. And it turns out that in R, when you implement these different methods, you actually implement them the exact same way. So often ANOVA is taught as this fundamentally different method of statistical analysis from linear regression. It turns out they're actually the same thing. Just one of them only incorporates categorical predictor variables. One of them typically incorporates continuous predictor variables. And you can actually create models that incorporate both in a linear framework. So the way that analysis of variance works is that we are comparing the means of different groups by partitioning the total variance across all of our observations into two sources of variation. The first is our within group variation. Okay, how much variation is there within each group? Versus how much variation is there between different groups. And if we find that we have much more variation between groups than we do within any single group, then we can be confident that there's a difference between their means. I guess another way of saying that is that if we find that the observations between different groups are more different than the observations within any single group, then we know that there's a difference in the means between those two groups. So the next few slides, I'm just going to walk you through how this works mathematically and really what's going on behind the scenes when we run an analysis of variance. And so first, here's just a little bit of the notation we're going to use. So we have our sum of squares within groups, which is going to be denoted as SSD subscript W. We have our sum of squares between groups, the amount of deviation that's between our groups. Then we have our total sum of squares. And so this is going to be our total deviation across all the observations combined. And it turns out that this is just the sum of squares within groups plus the sum of squares between groups. In this example, we have 3 different groups, group 1, group 2, and group 3. And I've colored them different colors just so we can keep track. It's just a little more obvious this way. And then each group has its own mean. So if we were to take each of these observations and there's a corresponding response. So in group 2, we found that maybe this response is plant height. One plant in group 2 was about 2.7. One plant in group 2 was about 3.2, maybe, and so on. If we were to take the mean of these heights, these plant heights in group 2, we'd find that there's a mean for group 2 around 3.2, and we could do the same thing for groups 1 and 3, and they have slightly different means from each other. And now here's the question, is whether these overall group means are sufficiently different from each other that we can conclude that these different groups actually have different mean plant heights. Okay, so maybe these groups were different fertilizer treatments. Maybe these groups were, we collected plants from different habitat types, or from different elevations, or from different temperature regimes, or something. Okay, but we have 3 different groups, and we want to know if their mean response, in this hypothetical example, the response is our plant height, is different. So to calculate the sum of squares within groups, again, this is our variance that is within each group, and we would do this for each group in turn. We start off by calculating that mean of that group, and that's what's denoted by this x bar I. Okay, so we have group I, in this case I would be equal to 2. So group 2, we have our overall group mean, and then we calculate how much each observation within that group deviates from that group mean. And so for each of these observations, we calculate how far is this response from the mean. So we would take maybe 2.8 something here, and subtract that from the group mean, square it, and then we add it to the next one where we take this observation, subtract that from the mean, This one, we take the mean, subtract it, and subtract it. So we get each of these deviations from the group mean, add them all together, and then we do that for each of these groups. And this tells us our sum of squares within groups. Okay, it's fairly straightforward. Next, we want to know what is the sum of squares between groups. And so for this, we have our mean for each group, again, but then we also have some overall mean across all the observations. And here I've denoted this using this sort of dashed line. So if we were to sum up all the observations, divide that by the number of observations, we get our overall mean across all these different groups, okay? Now what we want to know is how much does each group mean differ from this overall mean? So that's what we're calculating here with the sum of squares between groups. Okay, next we do something called normalizing these sums of squares depending on the amount of degrees of freedom for each of them. And so there's a different degrees of freedom associated with the within group deviation and the between group deviation. We're not going to focus too much on that, except for the fact that we need to know that when we calculate an ANOVA and we end up with an F statistic, which we're going to take a look at next, we just have two types of degrees of freedom for that F statistic. Okay, so when you are looking in the literature and you see that your F statistic has 2 degrees of freedom associated with it, 2 types of degrees of freedom, that's what they're talking about. Your within group degrees of freedom and your between group degrees of freedom. Okay, but now that we've calculated our between group deviations and our within group deviations, and these are now normalized depending on their degrees of freedom, then our goal is to compare how big is our between group variation compared to our within group variation. And this is just our F statistic. So we take the between group variation, divide that by the within group variation, and we get some ratio here. And again, we have 2 sources of degrees of freedom. We have our between group degrees of freedom, so the number of groups minus 1, and then we have our within group degrees of freedom, and this is the total number of observations minus the number of groups here. Okay, so we've arrived at our F statistic then, which compares our between group to our within group variation, and our F statistic can range anywhere from low values all the way up to high values. So if we have values close to 1, F is pretty small, this tells us, going back to this equation, okay, if F is close to 1, this tells us that our between group variation is pretty similar to our within group variation. And what that tells us then is that there really isn't a big difference between groups, okay, in terms of their response. But if F is very large, so our between group variation is much larger than our within group variation, then we can conclude that there is a big effect of group on our response. Okay? Groups differ in terms of their response. Now the question then is, how big is big enough to conclude that there's a significant effect? Okay, and again, this is where we use our test statistic, our F statistic. We're setting up a hypothesis test in this case. Okay, so our null hypothesis is that there is no difference between our groups. Our alternative hypothesis is that not all of the means are equal. Okay, so there's a difference in at least one of the groups from the other one. It could be that all the groups differ from each other, or that one group is very different from all the others, or 2 groups are different than all the others. Okay, but we have our F statistic, we have our degrees of freedom, and then we just need to compare our calculated F statistic to our F table. Okay, so previously we've used a T table and a chi-squared table. We're going to do the exact same thing with our F statistic to see how significant, how extreme is our F statistic. So there's 2 different ways we could do this, and as we did in the previous lectures with the t-test, the z-test, and the chi-squared test, we could do it the old school way, which is go to an F table. We have our test statistic, we have our degrees of freedom, and then we see, okay, well, how extreme is our F statistic at this level of degrees of freedom? And if it's very extreme, then we reject our null hypothesis in favor of our alternative, and that tells us that at least one of the groups differs from the others in terms of its mean response. Okay, so if our calculated F is greater than the F that we find in our lookup table for our degrees of freedom, we reject H0. So in our case, in the example that I had, I calculated my F statistic. I found 9.28 was my F statistic, and I had degrees of freedom of 2 and 9. Okay, so I had 3 groups, and 3 minus 1 is 2 for this first degrees of freedom, and then I had 12 observations and 3 groups, so 12 minus 3 is 9 for the second degrees of freedom. And then let's just go to our F table and take a look at how extreme is 9.28 for these degrees of freedom. Okay, so in this F table, because we have 2 degrees of freedom, it's organized just slightly differently than the T table we were looking at before. Okay, so here is our F table. We have our 2 sources of degrees of freedom. So one is represented across columns here, one is represented across different rows, and then I need to know what my alpha, my critical value is. Okay, so at what level is a p-value going to be considered significant for this test? And so very commonly people use this 0.05, but again, that's not a magic number. Okay, so 0.05 is actually a pretty low threshold for finding significant results. Okay, often in ecology it's set at 0.05, but sometimes you may want to actually set a much lower critical threshold to reject your null hypothesis. In this case, let's just go ahead and use 0.05. Okay, so my first degrees of freedom were 2. My second degrees of freedom were 9. So I go 2, I come down to 9, and I find that I would need to find an F value that was greater than 4.2565 if I wanted to reject my null hypothesis. Now, if we remember, my F value for this example was 9.28. Okay. So 9.28 is much greater than 4.2, and so in this case I would reject my null hypothesis in favor of my alternative. And so my alternative hypothesis is that there is a significant difference between my groups in terms of their mean. If we go back and actually just look at these different observations, just visually it's clear that there's probably a difference in the mean of this group versus these other two. It's not so clear that there's a difference between the red group, group 1, and the green group over here, group 3. Okay? And we would need to do a separate test, and I'll show you how to do that in just a minute, to see if there actually is a difference between red and green, a difference between red and blue, and a difference between green and blue. Okay, but so far our test statistic just tells us that at least one of these groups differs from the other two. So this was the old school way of doing it, going to a lookup table. In this course we won't do that very often. Instead, and what in your own research, you'll most often be using R code to do this, and it's much faster, much easier. It gives you a much more precise p-value. And so the way you would do this typically is with this LM function. This sets up a linear model. You can assign this to an object. So I would call this object LM1, and this object is going to be my linear model. I have my response, and then I use this tilde sign to say, okay, there's some effective group on my response. Okay, I'm testing to see whether there's an effective group on my response, which is Y. Then I have my data set. Okay, this runs the linear model. I can then print some summary statistics for it, and this tells me my p-value, tells me my F statistic, as well as my degrees of freedom. I can generate a classic ANOVA table using this AOV command. Okay, and then I can take a summary of this as well and get some more summary statistics printed out. So this is how you would do this in R, and we're going to do that in the lab this week. Now there's multiple different functions in R to generate ANOVA tables, okay, and to do an analysis of variance. The most general, the most useful in my opinion, is using this LM command, okay, for linear model. And so you specify this using a function here. So you say LM, and then you say what is your response variable, and it's a function of your grouping variable here. And we'll actually use this exact same formula, this exact same function, when we return to linear regression. It looks the exact same, which is why I feel like this is the most general and useful way to conduct ANOVAs, because you can also apply it to linear regressions, whether or not your predictor variables are categorical or continuous. You can also use this ANOVA command, and so this will generate this classic ANOVA table, but for this to work, it has to be you have to be using categorical variables, okay, instead of using either continuous or categorical variables. So I don't prefer to use this command very often. And you can also use this function, AOV, which stands for analysis of variance. Okay, and this essentially does the same thing as this linear model. It just presents the results slightly differently, doesn't work for continuous data. And so again, I prefer to generally use the LM function. And then if I want to print this ANOVA table and get some results that are specific to ANOVA, then I'll use this AOV command later. Now, so far we've been focusing on what's called a one-way ANOVA. And so this is where we're interested in the effect of one factor, one type of predictor on our response. And so now our predictor doesn't need to have only two groups. We could have one predictor variable here, say, that has 3 different levels. So this is our type of fertilizer we're using, okay? And there's 3 different types of fertilizer. So our fertilizer would be our factor, and we can have multiple levels within that factor, okay? This is still a one-way ANOVA. What effect does fertilizer have on our response? Maybe on plant height here. Okay, but often we may be interested in what are the effect of 2 factors at the same time and possibly their interaction with one another on our response. Okay, so this essentially gets at the question of, does the effect of one predictor variable, like fertilizer, depend on the level of another factor? Maybe this would be, say, the amount of light that we grow our plants in. Okay, so we would have 2 different factors here. In this example, maybe we have several different kinds of fertilizer that we're growing our plants, and we also have multiple different levels of light that we're growing our plants. Okay, so fertilizers and light is our 2 factors that we're interested in, and what is their effect on our overall response. So here in this case, we have, in this example, maybe we have 3 different fertilizers. We have group 1, fertilizer type 1, fertilizer type 2, and fertilizer type 3. And then for each fertilizer type, we've grown plants in different light conditions, low light conditions and high light conditions. And then we measure the response. Maybe this would be plant height. Okay, and what we see from this is that in our first fertilizer type, there really doesn't seem to be a difference in plant height whether or not we grow them in low light conditions or high light conditions. Okay, but our second fertilizer type, we see that first, in general, plants tend to grow better in our second fertilizer than our first one. And also, when we grow plants with our second fertilizer type in high light conditions, they tend to grow much better than under low light conditions. Now our third fertilizer type, we can see here, it's hard to tell if there's an overall difference just in general between how much plants grow in our third fertilizer type versus our second fertilizer type. But what we can see is that there's a very strong effect of light, but only when we use this third fertilizer type. Okay, so in this case, this is getting somewhat complicated, but we can see that there's appears to be a very strong effect of light, but only for this third fertilizer type. And this would be what's called an interaction. So our fertilizer type and our light level are interacting together to affect our overall response here, plant height. Okay, and this is what a two-way ANOVA is designed to address. And so we can even continue to make more and more complicated formulations of ANOVA type analyses, more complicated predictor variable structures. And it turns out it's actually quite easy to do this in R. All you do is, if you say you want to specify there's some interaction between our group and another type of treatment, okay, so maybe fertilizer and light level, you just use this little asterisk. This is a times operator, a multiplication operator here. And then maybe we have another 2 different types of predictors that are affecting our response, and you can actually put these together very easily in R, even though it might be very, very hard to represent this graphically, say using box plots. Okay, we're not going to deal with these more complicated ANOVA structures this week, probably at all in this course. Okay, and we won't even get into two-way ANOVAs this week. We're going to focus this week on one-way ANOVAs in the lab and what is the effect of a single grouping variable that might have multiple levels, but on our overall response. Okay, the last thing I want to touch on is the assumptions of analysis of variance. And these are essentially the same assumptions that are made by t-tests and z-tests, and the same assumptions that will be made by linear regression later in this course. The first one is that the observations are independent from one another. Okay, and what this means is that we don't have repeated measures of the same individuals over and over. Now, these second two assumptions we can actually have formal tests for, and we'll do this in the lab, but we want to first make sure that our residuals are normally distributed, okay, so that basically our observations are coming from a normal distribution. And the second is that each of our groups has equal variance. Okay, so what this means is that within each group, these observations should appear as though they're arising from a normal distribution, okay? And the means of these normal distributions can differ between groups. That's the whole point of ANOVA. But the variance of those normal distributions, okay, the variance of our samples here should be approximately equal, okay? All groups should have normally distributed errors, okay, normal distributions giving rise to each of these different groups. All groups should have about the same variance, and our observations should be independent. These should not be repeated measures of the same individuals. Okay, we can do a few tests for these, and we'll do this in the lab. So we would use a Shapiro-Wilk test for normality. This is very easy to implement in R. I'll show you how to do this in the lab. We would use a Bartlett test to test for the homogeneity of variances, okay? And that's just a fancy word for saying that the variance in each of our different groups is the same. And then lastly, if we have made sure that our assumptions are all correct, okay, so that we have normally distributed errors and that the variance in each of our different groups is the same, and if we do end up finding from our ANOVA that there's a significant difference between the means of our different groups, then we may be interested in, okay, well, which group is different than the others? Or which differences between groups are really significant? And this is where we're going to use a Tukey test. Okay, and this examines the pairwise differences between the means of all the different groups considered. Okay, we'll do this in the lab again this week, and the one that we are going to use is this GLHT function, and this performs these multiple comparisons simultaneously between all the different groups to tell us which groups truly are different from one another. So in our example, going back to our original example here, we found that there were significant differences, that at least one of these groups differed from the others. We weren't exactly sure, though, which groups were different from one another. So it's clear that this blue group has a different mean than red and green. It's not exactly clear if red has a different mean than green here, than group 1 and 3. And this is where a Tukey test would tell us which of these contrasts is actually significantly different. And I would guess that red and blue significantly differ from each other, green and blue significantly differ from each other, and I would probably bet that red and green do not differ from each other significantly. Okay, so the next step then is to go ahead and watch the lab video. I show you a few examples of how to run ANOVA and then how to run each of these tests to assess your assumptions for the ANOVA, and then to eventually do those Tukey tests to see which groups are different from one another. And then finally, go ahead and complete assignment 7, where we get into some more examples of doing this on real data.